In the previous screencasts, we've seen that the fundamental mechanisms that ensure energy efficiency during walking are an inverted pendulum during stance and a simple pendulum during swing. Although we've also seen that it's naive to see walking merely as a combination of these two. We started from a simple model of walking called compass gait, and in the last two screencasts we've seen how requirements for clearance and for adequate step length impose modifications on that simple pattern. We'll now look at how support is achieved, which requires us to look again at the inverted pendulum. When we last encountered this, we focused on energy. This time we're going to focus on force. These are the graphs of how the horizontal and vertical components of the velocity of the centre of mass change as the inverted pendulum operates. The centre of mass has to be travelling reasonably quickly in a forwards direction at the start of the movement because it's going to slow down as it gets higher and kinetic energy is converted into potential energy. It will be going slowest in the middle of the movement when the mass is highest, after which it picks up speed again as the potential energy is converted back into kinetic. We can also think about what is happening in a vertical direction. At the start of the movement, the centre of mass is moving upwards. As it moves around the circular arc that's dictated by the hip joint rotating about the ankle, then two things happen. In the first half of the movement, the body is losing kinetic energy, so the vertical as well as the horizontal components of velocity must reduce. But also the direction of movement flattens out, so a smaller part of that movement is in the upwards direction. These two effects reinforce each other, so that the vertical velocity reduces through the first half of the movement. It is actually zero as the pendulum passes over the highest point because just for a split second the centre of mass is actually travelling exactly horizontally. We can put this a different way and say that the centre of mass is decelerating in a vertical direction over the first half of the movement. After passing the midpoint, then the same two factors act in the opposite sense. The body gains kinetic energy, so starts moving faster, and as it moves around the arc, a greater proportion of its velocity is directed downwards. Both factors combine and the vertical component of velocity becomes increasingly negative, or in other words, it's accelerating downwards. Now, we said earlier on that we're going to talk around forces, and indeed we already are, because Newton's laws tell us that if accelerations are occurring, then forces must be acting. Let's think about what those forces must be. We'll look at the vertical component of the ground reaction on this graph, with body weight as our reference. Early on, the body is travelling upwards. It's got a positive vertical component, but it's getting slower. In other words, it's decelerating. The overall force on the body, therefore, must be acting downwards to slow it down. So the ground reaction acting upwards must be less than the body weight acting downwards. You can see that the slope of the velocity graph is getting a little more gradual with time, so the ground reaction must be getting closer to body weight over the same period. In the middle of the movement, the body goes over the top of the arc and from moving upwards to moving downwards, so it's still accelerating downwards. The ground reaction must still be less than body weight. The slope is at its gentlest, however, at this point, so the reaction will be closest to body weight. In the later part of the movement, the centre of mass is accelerating downwards. So again, the ground reaction must be less than body weight. And as the slope gets steeper, it must be that the ground reaction must be getting smaller. You can see that the ground reaction under an inverted pendulum is always less than gravity. I haven't been able to trace where, but I think Jacqueline Perry once referred to walking as a process of continuous falling. I don't know if she knew quite how biomechanically accurate she was being. But we have a problem here, because if the ground reaction is less than body weight throughout stance, then we are failing in the first requirement of walking. How do we get round this? Most of us will know that the ground reaction doesn't actually look like that predicted by the inverted pendulum. It's got two characteristic bumps. These certainly increase the ground reaction quite considerably above that generated by the inverted pendulum. We'll discuss the mechanisms for this in a later screencast. But look closely at the graph in relation to body weight. The ground reaction is only above body weight for a very short period, and by not very much. If we contrast this with the amount of time that the ground reaction is less than body weight, and look at the size of that deficit, you'll see that on average the ground reaction generated is considerably less than body weight. We are still not supporting body weight through stance. Here is the data plotted for left and right limbs. You'll see that the average vertical component of the ground reaction, the horizontal green line, is little over 80% of body weight. If we allow a short period of double support, however, you'll see that the ground reaction under the left and right limbs combine, and that the greatest total ground reaction acting on the body is actually just a little before the middle of double support, when two relatively modest individual ground reactions combine. The result of this is that the average value of the ground reaction is increased. We thus reach the conclusion that if we're going to rely on the inverted pendulum as the essential mechanism for moving the body forwards, then we will have to have a period of double support to ensure that body weight is supported. If the ground reaction was purely that under an inverted pendulum, you can work out that the double support period would have to be about 15% of the gait cycle. With a modified form of the ground reaction, we find in normal walking the double support period is about 10% of the gait cycle. One final thing. You may remember this slide from an earlier screencast. I said that it wasn't possible to have double support in compass gait because if the feet are in a particular position throughout and the knees are straight, then the body must also be stationary. In order to allow a period of double support and keep the body moving forward, we need coordinated movement of joints other than the hips, the knees and the ankles. To determine what that movement is, though, we'll need to consider how we achieve smooth transitions between phases of the gait cycle. And that will be the subject of the next screencast.